remember what is the probability, okay? And today we're gonna introduce one important thing we called normal distribution. And I'm pretty sure most of you guys already heard normal distribution, okay? Today I'm gonna introduce the properties of normal distribution and the definition of the normal distribution. Introduction to normal distribution and the standard normal distribution. Let's take a look at the definition. A normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is called the normal curve. A normal distribution is this property. The first thing is the mean, median, and mode are equal. Okay. Second, the normal curve is bell-shaped and is symmetric. About the mean. Okay. 3. The total area under the normal curve is equal to 1. Okay. 4. The normal curve approaches approaches but never touches the x-axis.
Never touches?
Oh, but it never touches, sorry. It never touches the x-axis. Okay. As it extends farther and farther away from the mean. Right? Now, the number 5. Between mu minus sigma and mu plus sigma, the graph curves downward the graph curves upwards or upward to the left of mu minus sigma and to the right mu plus sigma. Okay, so we have total 5 properties. The first things I want you guys to notice, what is a mu? Do you guys can recognize what is mu and sigma? Mu is what? What is mu? When you see the mu, what's that mean? Any idea? You forget it?
The mean of the population data set.
The mean, right? It's the population mean. What is sigma?
The spread of the data.
The standard deviation, right? Population standard deviation. What is x bar? Did you still remember what is x bar? What is S? I emphasize during the class when I teach you guys the different notation, right? One is about population, another one is about sample, right? So when you see the mu and the sigma, always about population, and the x bar and S is about sample, okay? So mu is a population mean, x bar is sample mean, sigma is a population standard deviation, and the S is sample standard deviation, okay? Deviation. So that's very common notations. If you learn the statistics, you at least when you see the paper or any newspapers, when you read the paper and see some statistics data, you should be able to know what is x bar s mu and sigma. Okay. Okay, now let's take a look at the properties. In order to help you guys to understand the properties of normal distribution, I'm gonna draw a picture. Okay. So the picture gonna be here. That is x-axis. Okay. Now let's take a look. The first property. The first property tells us the mean, the median, and the mode are equal. That means what? That means this value corresponding here has the mean, median, and mode. Okay. So the value here at this point represent the mean value, okay, mean value, median, and mode. I can write down as mu, okay, mu. This point, okay, this point. Be careful, is this point, okay, is this point. Now, that's the first property already indicate what is the mean value. The mean value is here in the middle, okay, in the middle, and the value mu on the x-axis is the mean value. Now, the second property tells us that is bell-shaped. A bell-shaped should be like that. Bell-shaped, right? Like a bell-shaped. And is a symmetrical about the mean. Symmetric. So for the mean, we have this axis goes through the mean, right? And it's very clearly this curve is symmetrical about the mean, right? It's very clearly. Okay, so that's the second property. The total area under the normal curve is equal to 1. What does that mean? I give you this curve like that, right? So it goes down, and the area underneath this curve is 1. Okay, is 1. Later, we're going to know the area underneath this curve is the probability, okay? So the area underneath the whole curve going to be, we include all the sample. That means probability going to be 1, okay? 1. Now, the fourth one. The normal curve approaches but never touches the x-axis, okay? So that means what? The curve goes down, goes farther away, always goes down, but never touches this x-axis, okay? The same things for this part, the curve always goes down, but never touches this x-axis, okay? Never touches. Always infinity close to the x-axis, but never touches, okay? So next time, if you see this guy, I give you guys an example. So next time, if you see, hi, I give you this kind of things, and somebody asks you, is that a normal distribution or not? No, because you can see the curve cross over the x-axis. Okay, that means that is not normal distribution. Not normal distribution. Okay, be careful. And of course, some curves, they look like that. Okay, it's very clearly they touches the x-axis. So it's still not normal distribution. And be careful, okay, not a normal distribution. And of course, if I give you a curve that is not symmetric, of course, that is not a normal distribution. It's not bell-shaped, it's not a normal distribution because we have a bunch of property here, right? It should be symmetric. If it's not symmetric, then of course, it's not a normal distribution. Okay, so let's take a look at the last property. Between mu and sigma, mu minus sigma, for example, here. Mu and sigma, you can see the graph curve downward. I didn't draw the picture very well. The curve is downward. That means what? I would like to draw another picture. Okay, make sure you guys understand it. So it's so it's here. Here's mu minus 6, mu minus plus sigma. Okay, so between mu minus sigma and mu plus sigma, you can see the curve. It looks like that, right? Like that. Okay, the curve always curve like that. So that means the curve downward. Okay, so if I give you a curve like that, it's curve downward, right? Curve downward. That's the meaning curve downward. Okay, and the curve at the left side of mu minus sigma, at the right hand side of mu minus sigma, we can tell the curve looks like that. Right? It looks like that. So the curve is upward. Okay. One is downward, one is upward. Okay. So remember the different shapes in different range or domain. Okay. So between these two values, the curve is curved downward. And at the left side of this value and at the right hand side of this value, we can see the curve is upward. Okay, so that's the 5 basic properties about the normal distribution. And I already assigned the homework. In the homework 4, there's a bunch of questions about the normal distribution. Okay, be careful. That's it. So that's the 5 properties. I wish I, through this figure, can help you guys to understand the normal distribution. Okay. Now let's take a look at some other important properties. So if I give you a bunch of the curve, okay, so let's take a look at this curve. We have three normal distribution, okay? And for these three, we can say the first curve here is very flat. And the second curve becomes sharper. The third curve, okay, I put a 1, 2, 3, okay? These three curves become sharper and sharper, okay, or become narrow and narrow, right? The curve is flat, become narrow and narrow, or becomes the shape becomes sharper and sharper, okay? So the only difference here is sigma, because they have the same value for the mean, right? We have the same value for the mean. The mean value is here, right? The only difference for this three is the sigma, okay? Sigma 1, sigma 2, sigma 3. And we can see the sigma 1 is greater than sigma 2. Sigma 2 greater than sigma 3. Okay, so what does that mean? As the sigma is decreasing, the curve becomes sharper and sharper. Sharper and sharper, or narrower and narrower, okay? Do you guys understand? So if the sigma is very big, okay, it's very big, that means it's very flat, okay? And if the sigma becomes smaller, and the curve becomes sharper and sharper, okay? Understood? That's the second important properties for the normal distribution. If you see a sharper normal distribution, so next time you can see that a guy has a very small sigma, okay, very small sigma. Now I'm gonna give you guys an example. Let you guys try it. Based on the property, I want you guys tell me. The first things I want you guys compare the mu A and the mu B, okay? Which one is greater? The second one is I want you guys compare sigma A and sigma B. Okay, try it. Which one is greater? Okay. please type your full name in your chat. I want to check your attendance. Thank you. Type your full name, okay? Full name. Thank you. You done? Okay. So which one is greater for the mu A and the mu B? Which one is greater?
It would be the one that's sharper.
Mu A and mu B.
It's mu A.
It's mu A, right? Because the value on the x-axis, okay, the mean value, according to the property, the mean value on the x-axis is the mean value. So the mean value for the B is mu B is here, right? And the mean value for the curve A is mu A, right? And the mu A is clearly greater than mu B. Is that clear? Based on the property we learned, right? The mean value is symmetrical of the curve is symmetrical with about the mean value. So mu A and mu B, right? And mu A is clearly on the right side of mu B, so it should be greater than mu B on the x-axis, right? X-axis. So how about sigma A and sigma B? Which one is greater?
Wouldn't that be B?
Good job, good job. Sigma B is greater than sigma A because what?
It's got a wider.
Yeah, wider or flat, more flatter, right? Than curve A, right? So as I mentioned before here, if it's a flatter or wider, that means sigma is bigger, right? Sigma is bigger. As your sigma decreasing, and it will become sharper and sharper. Okay, so that's a typical example tells you how to compare the mean value and the standard deviation sigma. Okay, so this time if I give you a bunch of curves, you should be able to compare the mean value and standard deviation sigma. Okay, just compare the value on the x-axis for the mean and compare check the shape of the curve to compare the sigma. Okay, sigma. Okay, now let's continue. We did a lot of work. Now, as we know, I give you guys a normal distribution. We know that this guy is n. N means normal distribution. So next time when you see a normal distribution, there's a capital N, you should tell that is a normal distribution. We use the notation N to represent the normal distribution. And for normal distributions, they usually have the mean value and standard deviation, sigma. Yeah. So I give a curve, and that is the notation. Okay, this notation tells you what is mean, what is standard deviation. Okay, so now I'm gonna give you guys another normal distribution, and that is a very special normal distribution. Standard normal distribution is a distribution with a mean of 0 and a standard deviation of 1. The total area on the normal curve. Normal curve is what? It's like that. For example, that is normal distribution. Okay, I draw this curve, and the normal distribution or standard normal distribution is a special case of normal distribution. Why is it special? Because this standard normal distribution has the mean value that is 0. Okay, so the first coordinate should be the mean value that is 0. Okay, so this guy is the mean value. And the second one is the sigma, that is 1. Okay, so sigma means the width. Okay, width. That is sigma, or we can use here is a sigma 2. Okay, sigma. Sigma is what? It's 1. Okay, it's 1. So that's the normal distribution. Of course, the area underneath this curve should be equals 1, because the normal distribution, as we noticed that before, all the area underneath the curve is 1, right? So the same things. For the special case of normal distribution is also a normal distribution. The area should equals 1. Okay, should equals 1. The area underneath the curve. Okay. And why we need to introduce such a very special normal distribution, standard normal distribution? Later you're gonna use it. Why? Because because the table. Okay. The table 4 always about standard normal distribution. Okay, be careful. Standard normal distribution. So if you see a normal distribution, you want to calculate any kind of probability, you couldn't directly use this table. Okay, you couldn't directly use this table. This table always about standard normal distribution. Okay, so if that problem is not about normal distribution, you couldn't use this table directly. Okay, you need to transform this normal distribution to standard normal distribution. Okay, that's the reason we introduce the standard normal distribution. It's gonna help you guys to solve the problems, to use the table. Okay, use the table. Otherwise, you couldn't use the table. Okay. So let's take a look some properties of the standard normal distribution.
Sorry, I have a question.
Sure.
Where it says on the X, the first sigma equals 1. On the other side, towards the negative, does it equal?
I mean the width. The width should equals 1. It's not about
They're both equal
the
to 1?
length. The length equals 1. The length always is positive, or the width is always positive, or the distance is always
It's
positive.
gonna be 1 and 1. If it's
It's the
1,
same.
it's gonna be 1 on the other side.
Yes, because the definition here is 1. That's the property from the figure. So if you define this guy is 1, so sigma, the width should be 1. Okay? So for all the standard normal distribution, the width or the length, okay? The length here should be 1, okay? Should be 1. Clear? Understood? Very good, very good. Property of the standard normal distribution. Mu equals 0, sigma equals 1. Okay. The first property, the cumulative area is close to 0 for z score close to z equals negative 3.49. Okay, that's the first. Second, the cumulative area increases as the z-score z-scores increase, okay. 3, the cumulative, okay, so here's z, the cumulative area for z equals 0 is 0.5. 4, the cumulative area is close to 1 for z-score, close to z equals 3.49. Okay, so let's take a look at these 4 properties. The first things we need to understand what is the definition of a cumulative area. Let's take a look, a picture. The cumulative area is what? Take a look. It's the definition. The cumulative area is the area to the left. Okay. Now let's take a look. If I give you a normal distribution, and I give you the z value, for example, z value here. I assume that guy is z value, okay, on the z-axis. Okay, so guys, I make a mistake here. So when you talk about the standard normal distribution, you always use the z, okay, use the z instead of x. For the normal distribution, you use the x, okay, use the x. And for the standard normal distribution, we usually use the z because that represent the z-score, okay, z-score. Okay, here we have z, and we have the normal distribution, n 0, 1, okay, n 0, 1. Now, the cumulative area means the area to the left, this part. If I give you a z value here, z0, and the cumulative area should be this part, the area to the left, okay, left, not right, it's left, okay. So that's the point, that's the point. Now, the second thing you guys need to understand, what is the z-score? Z-score is what? Z-score is, I think some of you already forget it. How to calculate the z-score? Should be x minus mu divided by sigma. We learned it, I think, 2 or 3 classes before, at least 3 classes before. So z-score, how to calculate the z-score? Z-score is the z equals x minus mu divided by sigma. So the z-score gonna help us to connect the normal distribution to standard normal distribution. Previously, we used x. Now we can use z through what? Through this z-score, because here is x. After subtract the mu divided by sigma, we're gonna get the z, okay? So z-score gonna help you guys to connect the normal distribution to standard normal distribution, okay? Later, I'm gonna help you guys to introduce the connection, how to do the transformation from the normal distribution to standard normal distribution. We're gonna use this z-score, okay, later. Now, let's take a look the properties, okay? Now we can take a look at these properties. So we understand the properties, okay? Understand the cumulative area. What's the meaning of the cumulative area? So we have, okay, and of course we have that is z, that is 0, that is a normal distribution. Okay, so the first property is what? Is this one. The cumulative area is close to 0 for z-score, close to this negative 3.49. What does that mean? What does that mean? You draw the normal distribution curve and find the value z equals negative 3.49. Okay, So I find this value. Probably is value here. Okay. And the cumulative area is the area to the left. Okay, the area to the left. This area is close to 0. Okay, it's close to 0. That means what? This curve is far away from the middle mean value. Okay, it's very, very far away. So it's very, very close to the z-axis, but it never touches, as I mentioned before, but it never touches, but it's very, very, very close to z-axis. And we can see the area should be 0, okay, 0. Now let's take a look at the second one. The cumulative area increases as the z-score increase. What does that mean? That means the z-score increasing. Okay, increasing, and we can say we increase the z-score, and the cumulative area gonna be increasing, right? If you draw another z, if you draw another z here, for example, here, and the cumulative area gonna be this the whole part, right? The whole part. So if we move the z1 or increase the z1 to the right, you can see the area is increasing. Did you see the second property, right? Second property. Now, third. So cumulative area for z equal to 0 here. Z equal to 0 is here, right? And the cumulative area is here. My question is, why is 0.5? Do you know it? Why is 0.5? When z equals 0, why this area to the left is 0.5? Any idea? The first thing is the area underneath the curve is what? The area underneath the curve is what? We just learned it. It's 1. Very good. So here is the metric about the mean value. So just half of the area. So that should be 0.5. Clear? Good job. Good job. So area should be 0.5 because that is half of the total area. Okay, when z equals 0, the cumulative area is 0.5. Clear? Understood? Very good. Very good. Now, the first one. The first one is the cumulative area is close to 1 for z scores close to 3.49. So we have another point is here. Okay, and the area to the left is close to 1. Why is that? Do you understand why is that? Why is close to 1? Based on the previous property, why this guy is close to 1? Do you know why? We can use the property from the number one, okay? Because, take a look, the cumulative area close to this guy is 0, right? Very good. Close to this guy is 0 because we is symmetric with respect to the mean value. So this area, of course, we don't call it cumulative area. Okay, we can see this area is what? This area. The area to the right is what? Because this is a symmetric, right? This part is 0. That means this part is what? Is 0 too, right? Agree? It's a symmetric. We have 2 little tail, area is 0, right? So when you see 3.49, the total area is what? The total area is 1. So 1 subtract this little 0 equals 1, right? Equals 1. So the area to the left should be 1, right? You understand? The total area is 1 because the area to the right is close to 0. So 1 minus 0 equals the area to equals 1. That is the area to the left. That is 1, right? Clear? Understood? So there's 2 important things you need to understand. The area underneath the curve should be 1. Okay? The area underneath the curve should be 1. And the second thing I want you guys to remember, the area, the cumulative area to the z-score equals 0, that is 0.5, because that is half of the total area. So that is 0.5, okay? So today we just learned these 2 important properties. I think I don't